Hello all y'all, I'm using a little bit different setup right now to make this video. Sorry you can't see my face, or I should say you're welcome for not being able to see my face. Today we're going to be looking at doing a little bit of linear regression review. Oh, this is a strong start. Alright, I'm just going to go, honestly if I were you guys, it wouldn't hurt you guys to pause the video, try the problem, and then see how I do it. Make sure y'all are staying safe out there. Try not to spread stuff to unnecessary people. This is unprecedented times. Alright. So let's look at, maybe I'll share a link where I got this stuff from too, and you can see, well, it's actually right here. Look up Mrs. Daniels AP Statistics, and you can steal her worksheets like I've been for years. Alright. So first thing they're going to ask you to do with this one is create and label a scatter plot. Alright, so I'm just going to put my dots in. I'm sure you guys will be fine. I'm going to put one up here though. And over here is going to be my long jump. Make sure, I'm going to put feet. You have to make sure you have the units in there. Make sure that these axes are labeled. Oh no. That's fine, I'll go like that. And down here we're going to put sprint, because we're looking at the correlation of sprint to long jump size. Remember, we're showing correlation, not causation. This is not an experiment. Alright. Labels are important. I don't know if you're going to have a free response part of your test, but who knows. Let's be prepared for anything. Alright. Scroll down. Now let's describe and interpret this scatter plot. Remember, when we're describing and interpreting scatter plots, we're using DUFs, right? D is your direction. Now if we looked at this, it would look like it was going down. So if it's going down, that is a negative direction, right? It's going up, it's positive. U is unusual. Okay? So that's outliers. Think about outliers. So for this one, we had one possible. If you actually looked, I kind of at that 8.09 151 spot, right? One possible. We don't know for sure, but it's definitely possible. F is form. And this is it linear or nonlinear, right? This one looked like a line, so I'd say it's linear. And S is going to be my strength. How much can it bench? Now, is it strong? Moderately strong? This one I would have said was moderately strong. When you looked at it, it looked like all the points. Moderately strong. Don't be afraid to use those adjectives. Alright. Now, what's the correlation coefficient? Alright, so remember, to calculate this stuff, I'm going to take these points. Okay, I'm going to use my calculator, right? I'm going to use my graphing calculator. And I'm going to go to Stat, Edit, and make this list L1 and this one L2, right? Then after I do that, I'm going to go Stat, Test, to lin reg t test. And that'll give me my R squared. My R will give me all my information which I need. Okay? So that'll be on your calculator. Now if you guys really need a calculator, I might be able to smuggle some out of the school. Okay? Super secret. I just said that on YouTube, so it's not really that secret. So when we did that, I got my R 0.74705. And remember, the closer you are to 1, the stronger. 1 or -1, because I guess this should have been negative, right? Because it's negative. The closer you are to 1 or -1 is strong. The closer you are to 0 is weak. Okay. Okay. Any questions so far? Can't hear you. All right, let's take a look at this beast. All right, a student wonders if tall women tend to date taller men. All right, so she measured herself and her dorm roommates and measured the men they date. That's what you do on a first date. You see how tall they are. All right, so now, first question. So remember ours, how much did they match up, right? So our first question would be, would R change if all the men were 6 inches taller? If all these go up by 6. No. Think about the graph, right? If here were all our dots, and we made them all 6 inches taller, it's still going to be the same correlation. It just shifts the whole thing up, right? I'm making all these hand motions like I'm on video, but I'm not. If anyone want... Alright guys, I just accidentally turned off my computer, but I'm back. Got to work. So, now what if we change all the heights to centimeters rather than inches? Again, it's going to be the same dots. It's just going to move where they are. Correlation, everything else will be the same. Alright, cool. I had to do all that restarting for that. Alright, let's look at some more examples to reteach you this. Let's look at this Honda CR-V. They give us a Scatterplot. It's the blah blah blah, right? So now, first thing I want to do is read that. It's about used CR-Vs and their cost based on miles driven, right? So first thing I'm going to do is calculate that correlation. Again, I'm going to go to Stat, Edit, make this L1, this L2. Then I'm going to go to Stat, Test, Lin Reg Test, and that'll give me my R. This one I get R is negative 0.874. So what does that mean in plain English? It means that there is a strong negative correlation between cost and miles driven. Wow, in a Honda CR-V. Right? Okay. Again, pause it, try it yourself first if you want to see what you're doing. I'm going pretty fast. What's the least squares regression for this? So again, I did this in my calculator. Stat, edit L1, L2, stat, test, Lin Reg Test, and I get, remember you're looking for the phi y hat, predicted y equals your b minus ax, if you want to think about it that way. But for this one we get y hat equals 18773 minus 86.13x, where y hat is predicted, remember it's not for sure, predicted cost or price, and x is miles driven, right? Now what is my y-intercept? Well, your y-intercept is this piece right here, right? What does that mean? That means if we had a CR-V with 0 miles, and then it would cost 18,007. Bye guys. $18,773. Does this have any real world implications? No, because you're not going to buy a car with 0 miles, especially a used car. This was a 2005, 2009. So you're not going to find a used car with 0 miles. So that makes no sense. Now what's my slope? My slope is negative 86.13. Does this have any, what's it mean in context? For every Is this in 1,000 miles? Let me check. Yeah, that was 1,000 miles. I'm sorry. I should have said that before. Because this in thousands, right? Every 1,000 miles. Because every mile taken off $86 is, yeah. For every 1,000 miles driven, cost decreases by $86.13, right? Does this have any real world implications? Yeah. For every 1,000 miles you drive, the value of your car drops by $86. Okay, so that's 100% real world application. All right. Let's talk about one more thing actually on this one. It's not on here. But let's say I want to talk about residuals using this. Oh, I need that equation. So a lot of you guys were asking, I don't have a question on this. What if I make up a new question over here? Well, if I said, what? You buy a car with, I don't know, 1,000 miles. I am making it. And it costs 19 grand. What's the residual on that? So residual is actual minus predicted. Okay, so for this one, I would do my actual is 19 grand minus, I'd plug in 1,000 to this equation. When I plug in 1,000 in this equation, yeah, what? That moves over. Oh, 1,000 miles. So I'd plug 1 into the equation, right? And that's like 1860 something. I'm just going to put 1860, sorry. And I got 400. So that means that the cost of my car was $400 above what was predicted. Okay, so that's what a residual is. Hey! Go ahead and read that for a second. So, they're looking at sugar and freshness. More sugar means more fresh and delicious. It makes you feel bad on the inside. Sorry, this is really loud. There's just so much life going on in here. So they did a scatter plot. They put their line in there. This is a residual plot. This is how far away each of the actuals were from the predicted. Like the actual from predicted, right? Actual from predicted. It's kind of like the length of these lines, right? And then they graph them on here. Okay? Now remember, well, we'll talk about it. And then we got the computer readout here. Now for this one, we don't have to use our calculator. They gave us everything to do it. So what's the equation of least square lines? The constant coefficient is going to be your y-intercept. Okay? So that's going to be the 181.2, right? Plus your slope is going to be your coefficient of whatever your variable is, or sometimes they'll call it it's whatever you're looking at. So it's 15 times sugar, or x. And that will equal my y hat, right? My predicted. Remember the hats always mean predicted or stat. Okay. We have to define them. Y hat would be predicted freshness. Make sure you put predicted. Okay. And x is going to be your and sorry, I had to deal with something. X is your sugar content in whatever they measured it in. Tablespoons. Tablespoons, right? TBS. Is a linear model appropriate for this? Yes. Yes, it is. I just put yes on my paper. Nice job. Yeah, because look at this. 2 reasons why. Number 1, this is random. Remember, if it's random, it's linear. If it looks like a parabola, it means it's nonlinear. And the other thing you could also say is your r, well, that's r squared, but if you square root that, it'll give you your r is also very high. So it's definitely linear. Yes, and it looks like a line. So that's 3 reasons why. Biggest reason is the random residual plot. What's S mean? What does S mean? Wait, I have a keyboard. I'm going to type it. That's only available in Pro. I ain't got Pro. They offered me a deal, but it's not working. So my S is 7.52596, right? That means that our prediction is off on average by 7.52596 hours. Okay, that's just your standard deviation. That's how far your predicted is usually away from your actual. What's r squared mean in this context? R squared, remember r's correlation coefficient. R squared is your variation percent in a way. So you would say that 86% of variation is explained by this model comparing hours of freshness to sugar content. Well, guys, I hope you found this useful. If you didn't, just let me know. It's okay. Stay safe out there. Make good choices. See you on the flippity flop.